components. Now, once we have that, next process is designing those structural components so that whatever forces comes on the structural component, it can withstand them. And that is the focus of these lecture series. Now, once the design is done, then you need to represent your design through a language that can be understood by the people who are actually executing the structure. So your design is to be conveyed in terms of through drawing. Now that drawing goes to the construction site and the people involved there do the construction, and finally you have. So if you see your curriculum, civil engineering curriculum, you learn each of these steps as separate courses, and then probably towards the end of your civil engineering curriculum, when you do project, you try to assimilate all these concepts together. When we talk about design, you see, when we talk about design, one of the important thing that we need to decide at the very beginning is the material. Means the structure will be made of which material. We can have various civil engineering material. For instance, I try to give here some of the examples of very well-known structure made of different materials. We have steel structure, we have concrete structure, we have masonry structure, we have wooden structure. We can have composite structure as well. For different material, your design philosophy will be different. At the very beginning, one thing we need to finalize is the material. In this course, we'll concentrate reinforced concrete. Concrete as a material, concrete is very strong in compression. When compression comes, it can resist the compression, but when tension comes, as you can see here, it hardly takes any tension as compared to its compressive. So what happens, for instance, if you take a beam, a simply supported beam subjected to transversely loaded, subjected to transverse load, then the beam may deflect like this. If the beam deflect like this, then from structural analysis concept, we know the top fiber of the beam will be under compression and the bottom fiber of the beam will be under tension. And as I just now said, concrete is very weak in tension, so concrete cannot take those tension, therefore cracks develop. Whereas the compression phase, it's still this tension, since concrete cannot take the tension, we need to enrich the tensor. In order to enrich the tensile resistance of a structure, we need to put something which can take the tension, and here the something is reinforcement. Means the concrete is reinforced with something so that the entire structure can take tension and compression both. The compression primarily taken by concrete and the tension taken by. So we have composite structure where concrete is a mat and which is reinforced by. Now just I would like to spend 2 slides on concrete. I believe that you know what concrete is and how to prepare concrete. It's a mixture of, or proportionate mixture of, various ingredients. We have cements, we have fine aggregates, we have coarse aggregate, then water, and then we mix together all of them to get the concrete. And then we have steel bar. Mainly we have 2 different kinds of steel bar. One is mild steel and another one is high yield strength steel. We'll discuss in detail about their property, but these are the main 2 bars are used in reinforced concrete structure. Now the objective of this course is, we have concrete as a matrix and then steel as a reinforcement, and we mix them. If we put them together, we have reinforced concrete. And now objective of the course is, once we have this reinforced concrete, using this reinforced concrete, how we can design these different kinds of. So we'll try to give a very brief introduction to this process. There are different design philosophies. You remember, I am not saying design methods. It is design philosophy, because see, for same structure, different people can have different kinds of design. Okay, so we'll pose the design problem as an optimization later in this course, but there are mainly 3 different design philosophies. One is working stress method, which is the oldest of among these 3. Then load factor method. This is also known as ultimate load method. And finally, the recent one that we practice today nowadays is limit state method. And our focus of this lecture series is to highlight the different aspects of limit state method. Those who are interested in working stress method and load factor method, for comprehension or for better understanding of the better appreciation of limit state method, I request them to go through any design of RC structure books. You will get a brief introduction of these methods. But as far as this lecture series is concerned, we will only concentrate on limit state method. Okay, these are the books. There are many other books available in the market, but I found these books give you a reasonable discussion on theory as well as examples. So it is good to have a copy of this. Well, Emma, other than apart from these books, we will be also using some Indian standards, some Indian standard code. The two codes that we'll be using mostly in these lecture series is IS 456 2000 and SP16. IS 456, as you can see, it is a plain and reinforced concrete, and SP16 is a special publication. It's a design aid. If you have to design, you need some of the important parameters. Those parameters are, it is always important to have a copy of at least this code IS 456 2000, because you will be using it extensively. See, what is limit state? Limit state, as it is written here, a structure is said to have reached its limit state when the structure as a whole or in parts becomes unfit for use. You see, to give you an example, suppose you use a chalk to write something on the board. Now, as you keep on writing the chalk, initially chalk has certain length, but as you keep on writing, you keep on using the chalk, the length of the chalk gets reduced, and you will reach a state where the length becomes so small that you cannot hold the chalk properly. What we can say here is the chalk has reached its limit state. Now, this limit state we need to define. What is the limiting state of a structure? In this case, suppose for the example that I given for a chalk, the limiting state is the state beyond which the chalk cannot be used. The chalk cannot be used because I cannot hold the chalk. Limiting state for a structure is, it's a state beyond which the structure as a whole or in part, it cannot be used. It cannot serve the purpose for which it is designed. There are different kinds of limit state. We'll discuss them as we proceed. Now, limit state design philosophy is the structure needs to be designed in such a way that it does not reach any of the specified limit state. Specified limit state, just now I mentioned that there could be different kinds of limit state. What limit state you specify, depending on that, the design philosophy structure should be designed in such a way that the whatever limit state you specify, it should not reach it should not reach those limit state during the expected life of the structure. Now let us see what are the limit states we have. Mainly we have two different limit states. One is called limit states of collapse. What it says is the structure as a whole or in part, it should not collapse. It should not fail during the expected life of the structure. The structure should be safe during its expected life. This is the first limit state. Another limit state is limit state of serviceability. See, what may happen is the structure is safe, but for some reason, for instance, the structure becomes very unstable, or the some parts of the structure is excessively deflected, or there are cracking in the structure. For some reason, even the structure is safe, it doesn't collapse, the structure cannot be used. The structure cannot serve the purpose for which it is designed, and that is called limit states of serviceability. Now, what are the different serviceability limit states we have? For instance, this excessive deflection, structure should not deflect excessively. Durability, structure should be durable throughout its lifespan at least. Then there should not be any cracking in the structure. The overall stability of the structure should be maintained. Structure should not become unstable. And then of course, if in case of fire, then structure should be able to what happens, the structure is still safe, structure doesn't collapse, but again because of the fire, some components of the structure is damaged, so as a whole it cannot be used. So these are some limit state of serviceability. So we have primarily two limit state. One is limit state of collapse, which says the structure should be safe, it should not collapse during its expected life. And the another limit state is limit state of serviceability, means the structure should be serviceable. It should serve the purpose for which it is. Now you see, IS 456 2000 gives you some brief discussion on these different kinds of limit state, and I tried to give the clause number. um limit state of collapse. uh, um, Limit state of collapse, again we can have, suppose if we take a structure, if we take a beam for instance, the beam, we can have bending in a beam, we can have shear force. Any structure may be subjected to compression, a structure may be subjected to torsion, the structure may fail in different modes. Okay, it may fail in flexure, it may fail in compression, shear, it may fail in torsion. These are the clause which discusses different limit state of safety or limit state of collapse. Similarly, the clauses which discuss the limit state of serviceability are is these: the durability limit state discussed in clause number 8, overall stability clause number 20, fire resistant clause number 21, deflection clause number 42, and cracking clause number 43. So since this is our first class, so what I suggest you, when you come tomorrow, at least get a copy of IS 456 and find some time to go through these clauses. Well, see, from engineering perspective, yes, there are two limit states. One is limit state of collapse and another one is limit state of safety. Is important, is the first priority. Structure should be safe under any circumstances. The second is structure should be serviceable. But there is a third component in design as well, and which is economy. So we need to design a structure in such a way that it is safe, it is serviceable, and it is also economical. I try to give a illustration of what the economy means. Suppose I want to make a chair. If you take this chair, is safe and serviceable. A good designer uh, come up with this design instead of this. Both are safe and serviceable, but this one is economical as well. So design is an optimization problem where you need to find out the most optimized structure which is safe, serviceable. That's what I said, that now this optimization, the requirement of the weightage to safety, weightage to serve. For instance, if we talk about some of the structure which are very important, say for instance the nuclear power plant, or some of the offshore structures, important buildings, they are the more concentration, more focus has to be made on safety and service. Some of the structure, safety and serviceability is important, but economy is also important. For instance, you are making you are design structure for say Indian villages. Okay, you are preparing low cost. You are designing low cost houses for poor people. In that case, you cannot really. You need to think about a material which are easily available, so that the structure becomes your economical. Okay, so you need to as a design engineer, you need to consider all of them: safety, serviceability, and economy. Safety and serviceability that are given in IS 456, it is based on certain mechanics, and we'll discuss that here. But as far as economy is concerned, that you need to apply your judgment. Now, before we come to the actual mechanics, we need to define few things. First thing is the characteristic load. You see, suppose you make a structure, you design a structure for certain load, but nature is very complex in nature, it's very uncertain. So you really cannot say that this is the load, precisely this is the load is going to come on the structure. There may be some uncertainty, there may be some slight variation in the. So when we talk about load, instead of deterministically say that this is the amount of load that is going to come on the structure, we use a probabilistic definition of the load, and that term is called character. And what is the characteristic load? Characteristic load is the expected maximum magnitude of the load that the structure has to withstand. For instance, if it is dead load, then the characteristic load is the load, the 95% of the the probability of having that load is 95%. There is a 5% probability that the load exceed that particular value. So if that value is called the characteristic load. For instance, but this 5% again depends on whether you are talking about dead load, wind load, or any other load. For instance, if we talk about wind load depends on wind speed, right? Now, characteristic wind speed is probability of having that speed is 98%. There is a 2% chance that the wind speed is more than that, and that value is called characteristic load. Calculated from that characteristic, that wind speed is called characteristic wind. So characteristic load is the expected maximum magnitude of the load. There is a little uh, there is a little percentage chance that the load may exceed of that value, but that percentage is very small. In case of dead load, it is 5%. In case of wind load, IS 875 different parts gives you the characteristic load for different kinds of characteristic load. For instance, IS 875 part 1 gives you dead load, part 2 gives you live load, and so on. If you want to find out characteristic load, dead load on a structure, see the IS 875 part 1, it gives you the self weight of different kinds of material. If you want to see the characteristic live load on the structure, you see IS 875 part 2, which gives you live load on different kinds of structure. For instance, whether the structure is an office building, residential complex, or any other industry building. So whatever live load comes on the structure depends on the purpose of the building as well. So the I 875 part 2 gives you the characteristic load on different kinds of building. Similarly, wind load is given in part 3, snow load is given in part 4. Earthquake is given in a different code, which is IS 1893, 2002. We may not directly use all these codes in this, codes. The only code that we'll be using is IS 456 and probably SP16. These are, we are discussing these for your information, so that we can have a comprehensive information about the design. We have discussed load. Okay, we need to design structure such that whatever load comes on the structure, it can. So naturally, we need to discuss about the strength of the structure. Again, strength of the structure is also a probabilistic in nature, because suppose you are making concrete. I believe that all of you had, if you had concrete lab, we mix several ingredients together to get concrete mix. Now, when we mix them, then we, at every stage, when we procure material from, we weigh them, we mix them, at every stage, we contribute some amount of variation, some amount of and therefore, the finally, if you test 100 cubes, 100 concrete specimen, it's not that 100 times you will get the same result. There will be some statistical variation in the result. Okay, so we cannot really say the maximum of all the ladders is the strength of the concrete. Then this will be the overestimation of the strength. We can also not say the minimum of the strength will be the strength of the concrete. That will be the underestimation of it. So similar to the characteristic load, here also we need to go for some probabilistic definition of strength. And that definition, that is called characteristic strength. And for concrete, what is characteristic strength? I'm talking about compressive strength of concrete, because the concrete RC structure, the concrete is primarily, the purpose of concrete is to take the compression. That's why we always talk about compressive strength of the concrete. Wherever you talk about strength of concrete, it is implicitly mean it is compressive. Now, compressive strength of the concrete is the strength below which not more than 5% of the test results are expected to fall. So, if you test 100 specimen of the same concrete, then 95 times, for 95 specimen, you will get the strength. There is a 5% chance that the strength of the concrete will be lesser than. Then that value is called characteristic strength of compression. Now, since in RC structure we have two components, one is concrete and another one is steel. So we need to also define what is the characteristic. If you remember in the beginning, I showed you two different kinds of steel. One is mild steel, and another one is high yield strength steel. Those who have already solid mechanics background, or understand what is the stress, what is the strength, and how the strength of any material can be represented through stress strain curve. This is the stress strain behavior, a typical stress strain behavior of different steel. Now, there is a very interesting thing to observe here. One is, you see, this is for mild steel and this is for high yield steel. Now, what happens in mild steel, what you can see is, initially the stress, this is strain and this is stress. Initially the stress strain relation is almost linear. Okay. So stress is linearly proportional to strain, and the slope of this linear segment is called Young's model. Now then, when the stress reaches a certain value, then the even after increase in strength, even with increase in strain, the stress remain almost same. So we have a plateau region. This it says that initially when the material made of this steel is loaded, then this relation between strain and stress is linear. So with increase in strain, stress is also increased linearly. Then when the stress reaches a particular value, then that linear relation no longer remain. Then in this case at least, your even with increase in stress remain. This zone is called plastic. So up to this it is elastic, means uh, if in this segment if we remove the load, then again the material goes back to its original configuration. But after that, when it reaches this point, it goes into plastic zone, and then if we remove the loading, it doesn't go back to the original configuration. We have some permanent deformation in the structure, which is plastic deformation. And this point beyond which that after that point the material goes into plastic zone, this point is called, the stress at that point is called yield stress, and that is denoted by Fy. Now if you see mild steel graph, then it has a very well defined yield stress, whereas if you see this graph, this stress strain behavior, initially it is linear, absolutely fine, then after beyond certain point it becomes non-linear, and this nonlinearity is still maintained. It goes into plastic zone, but unlike the previous case, it does not have any well defined. So we can just by this stress strain graph, from this point we can say that yield strength of mild steel is this, but just by from this curve we cannot say what would be the yield strength of. So what we do, the standard practice is we draw a line which is parallel to the initial linear line, and this line is drawn at 0.2% strain, and this 2% strain, if we draw this line cuts this stress strain curve at this, and this point is called, the stress at this point is called stress corresponding to 0.2% proof stress. So we will not go into detail of what is proof stress, why it is called proof stress, why 0.2% is taken. Those who are interested, please go through the literature to find out why this 0.2% is taken. Dewis will take this 0.2% for granted. Now the characteristic strength of steel is this. If it is mild steel, then this is the characteristic strength, but if it is not mild steel, if it is high tensile strength bar, then which does not have well defined yield point, we take the yield stress is equal to the 0.2% proof stress, means the stress which correspond to the 0.2% yield characteristic strength, yield stress or yield strength of. Now the standard notation that we use for concrete is FCK, which is the characteristic strength of concrete, and the notation we use for steel is Fy, characteristic yield strength of steel. You may be having some doubt on this slide. If you have, after the end of the lecture, we can again come to this slide and discuss further. So what we have discussed so far is characteristic. Now let us discuss two more terms, which is design load and design strength. Design load, and there also we introduce partial safety factor. Design load is characteristic load into the safety factor for load. Okay, why it is called partial safety factor, I'll come to this point. So you know that what load may come onto the structure, but you design the structure for more, design the structure in such a way that it can take more load. So that you can do, and that load is called design load, and that is obtained by multiplying characteristic load by some safety factor. Now IS4, this is the snapshot taken from IS 456. IS 456 table 8 in clause number 18.2.3.1 gives you the partial safety factor for different load. DL is dead load, then we have wind load, we have live load. If it is dead load plus live load, then safety factors are different. If wind load we have in common in addition to dead load and live load. you have different safety factors. So when you start design, the first thing you need to do is the fix the material, decide the material. When you decide the material, your characteristic load is freezed, characteristic strength is freezed. When you decide the purpose of the structure, your characteristic load is also freezed. Now, once you know this characteristic load and characteristic strength, you need to find out what is the design load and what is the design strength. Means design needs to be done for this for design load, and design load is obtained by multiplying characteristic load with partial. So in this case, what exactly you are doing? You are overestimating the load. Overestimating the load means you are making the structure more safe. Your design is more conservative. Then we have design strength. What is design strength? Design strength, you know the characteristic strength of material, and then design strength is obtained by dividing characteristic strength by partial safety factor for strength. Means you are underestimating the strength of the material. So in both the cases, when you first you overestimated the load, so you are actually making the structure more safe, and here you are underestimating the strength, means the structure, the material can take more load, but still you are assuming that the strength of the material is less. So again, here also you are making the structure more safe. Now we have two material in as you see here in this figure, different, we can have dead load, live load, wing load, or any other kind of load. For different load, we have different load factor. Similarly, we have two material here. One is concrete, another one is steel. We have two different safety factor. For concrete is 1.5. Now you may ask the question that why concrete safety factor is more and why steel is less. The answer is a very practical reason, because steel is manufactured in a very controlled environment. Okay, so if you buy steel even for different manufacturer, the variation in strength is very less, whereas the variation in concrete strength is much higher because it is not made in controlled environment. You buy aggregate, these are all natural product, natural material, right? Aggregate cement, aggregate sand, you buy them different sources, and when you buy them from different sources, you have some variation there. Then you mixing, how you are mixing it, you are mixing different kinds of water. So at every stage you introduce some kind of uncertainty. Therefore the uncertainty concrete strength is more. Therefore the factor of the partial factor of strength for concrete is higher. Now go back to my first point, why it is called partial safety factor. In order to understand, appreciate that in a more better way, I request you to to at least spend half an hour time on working stress method and ultimate load method or load factor method. You see here we have factor of safety, but these safety factors are different for different scenario. We have different safety factor for load, we have different safety factor for strength, and even in strength we have different safety factor for concrete, different for steel. Even in load we have different safety factor for dead load, live load. That is the reason why it is called partial factor of partial safety. So next is, you see, nature is very complex phenomenon. The when we study any physical process, what we do is, the first thing we do is idealize the natural phenomena. We cannot, it is very difficult to study nature the way it is. We need to idealize it. Okay, we need to or instead of idealization, idealization is a valid word, but I would say you need to simplify it, okay, so that it can be used in a very efficient manner. And here also the important part here is the what is the strength of concrete and what is the strength of. Now you see, this is the experimentally obtained stress strain behavior of, you can see that initially it is non-linear anyway, then it reaches an ultimate load, and then then the strength. And if you take different grade of concrete, and you have different grade of concrete, means concrete having different strength. Okay, you have generally grade of concrete is represented as M. When we say M15, means the strength of the concrete is 15 megapascal. M for mix. And then if it is M25, the strength of concrete after 28 days is 25 megapascal. I believe that you all know this terminology. Now But when we in the design we don't take the exactly stress strain behavior that we obtain from experiment. We use an idealized curve for concrete, and same thing for steel as well, or rather a simplified form of this stress strain behavior. Okay, and what is this simplified form? This simplified form or idealized form is shown here. What you can see from this from this test and behavior, though we have for different grade of concrete we have different maximum strength, but more or less for all concrete the maximum strength occurs almost at the same. So irrespective of the concrete you have, irrespective of the strength of the concrete you have, more or less the maximum strain that the concrete can have, compressive strength, is almost similar. Now at this point I want to make one thing very clear. uh, we'll discuss some of the assumption of limit state design as well later. Whatever we are discussing here, the motivation of motivation for this idealization and motivation for most of the assumption that we use in limit state design, they are based on observation through experiment. So they are not ad hoc they are not ad hoc assumptions. They are they have a very strong experimental evidences. Okay, so this is one example. These are the experimental evidence that irrespective of the concrete, they reaches the ultimate strain almost at the reaches the ultimate state at the almost at the similar strain level. Now what this idealized curve says. Idealized curve says that you start from 0, your stress strain behavior is parabolic, and this is parabolic up to a strain equal to 0.002, and then beyond that point you take a constant curve, and even if it is constant, the maximum strain the concrete can have is 0.0035, and if your compressive strain is more than that, then the concrete fail, and which is very evident from this figure. It is almost at 0.0035 you reach the maximum value, and up to this point, up to 0.2% up to 0.002 strain, you take the parabolic, and from there you assume it is constant. It is constant up to 0.0035, and beyond 0.0035 concrete fails. Now this is the idealization of exactly the same curve. Now one assumption is that the assumption is highlighted in a box, that compressive strength of concrete in structure is assumed to be 0.67 times the characteristic strength. Now here I introduce one point is called size effect. You can wrote down the term size effect. We won't discuss here in this lecture series, but that's a very interesting concept. And I suggest you go back and Google size effect of concrete and see yourself some of the interesting results. What it says is the size effect, as name suggests, the effect of size, right? It says that you test a specimen in lab. There is no guarantee that the same material, when it is used in actual structure, it will give the same strength. It is observed that when it is used in actual structure, larger structure, the strength gets reduced. There are different reasons for this size effect, but this happens. Now therefore what IS 456 says is, you obtain the strength FCK, which is the characteristic strength of concrete. You obtain from laboratory some value, but when it is used in actual structure, you reduce the strength. And what is the you take the 2/3 of this, the strength of the concrete when it is used for actual structure, used as 0.67 times of. Now then on top of that you have partial safety factor for concrete. The partial safety factor for concrete is 1.5. Instead of taking these as characteristic load, you take these as characteristic strength, you take these as characteristic strength of concrete used in actual structure, and in addition to that you apply the partial safety factor of 1.5. So this is your designed curve for. So this is experimentally obtained curve. This is idealization of experimentally obtained curve. From this to this we have reduced the strength, because you cannot get the same strength when the same concrete is used in actual structure. So you reduce the strength. So this is the characteristic strength of this concrete used in actual structure, and then further the strength is reduced to get the design strength. by dividing characteristic strength. Okay, so again, if you have doubt or if you have any confusion on this graph, we can come back to this and discuss, because these are the things, these are the building blocks of your linear state design. If you have any question, any confusion in this graph, it is better to clarify. Okay. Uh, Now next is design strength for. Here we have given two different kinds of steel. One is called mild steel and one is cold work deformed bar or high yield strength bar. You can see that mild steel has well defined yield point Fy, and but in this case we don't have any well defined yield point. So yield point you take the yield stress is which is at 0.2% yield stress, which is called proof stress. Now this is the idea, this is your test and behavior for steel, idealized test and behavior, and then you use factor of safety, partial factor of safety for material strength for steel, which is again 1.15, if you remember 1.15. So you substitute, you give 1.15, so you get, this is the design strength for steel, design test and curve for steel. So we have, this is the design strength for concrete, and this is the design strength for, this is the design strength, design test and curve for steel. Okay, we are almost we are almost have sufficient information to start the or to discuss the design philosophy. But before we do so, even if we talk about RC structure, in any RC structure there are different components, right? For instance, if you take a residential building, in the residential building we have, or for that matter any reinforced concrete building, we have columns, we have beams, we have slabs, then we have staircase, we also have foundation. So design, when we design a building, it means we need to design every components of the building. We need to design for column, beam, slabs, each and every components. If the building has shear wall, we need to design shear wall. Lift core, we need to design lift core. Each and every component needs to be designed. Design method for, or the design consideration for different structural components is different. Okay. So again, in this 5 hours lecture time, it is very difficult to discuss the design concept of all the structural components. What we do here is we'll discuss the design philosophy only for beam. The reason why we chose beam is, we'll see later, that that the concept of beam can be extended to other structural components as well. For instance, if we know how to design a beam, we can, with very minor modification, we can design a staircase. With very minor modification, we can design slabs. Again, with very minor modification, we can design. When we say that we are designing, we'll be discussing the design of beam, it actually it means that we'll discuss the concept of all the structural component which can be idealized as beams. And the structural components which can be idealized beams are your slab, staircase, foundation, or many other structural components that we'll discuss on the last. Now we'll start how to design. Just before we actually go to the finished design of beam, I try to give you some of the structure which can be idealized as beam. Say beam is, when we say beam, it's not only confined in civil engineering literature. The many structure can be idealized as beam. For instance, if this is a civil engineering structure, yes, it can be idealized as a beam. But for many other structures, say this also can be idealized as a beam. An aircraft can be idealized as a beam. Boom can be, a crane boom can be idealized as a beam. A missile can be idealized as a beam. Even a badminton racket or cricket bat can be idealized as a beam. A range can be idealized as a beam. A ship can be idealized as a beam. Even at the electro, these instrument is used to determine the surface of a specimen, which is the size is in terms of mm. What is done is, we have a small cantilever beam which vibrates, and every time it vibrates, it tries to sense the profile of the surface, and the size of this cantilever beam is in terms of a fraction of mm, or sometimes it is mm. So this also can be idealized as a beam. So when you say beam, beam is a concept, is an idealization. It is nothing to do with civil engineering. But as far as this course is concerned, we'll discuss beam, or we'll view beam Before we proceed, there are a few questions. We'll spend 2-3 minutes to address them. First question is for a particular steel. If we know the strain, how do I find out the stress? To answer this question, suppose this is the stress strain behavior. Now this is the stress strain curve for steel. Now if we know the strain at this point, so you corresponding stress will be, this is the corresponding stress. If you know strain at this point, the corresponding stress will be this is the corresponding stress. Don't go by these dots. These dots are given to explaining the proof stress, concept of proof stress. But for a particular strain, for instance, if we are here, then the strain will be this, means this plus this. Okay. So the getting the stress for a particular value of strain is same. The method is same that we follow in any curve. Any curve, if you know x, if you know the function fxy, how to get y. Now there are another example why beam idealization is required. We'll discuss that later. There is another question is example of live load and imposed load, that also we'll discuss at the time of design. There is another question, difference between HYSD bar and taut steel. When we come to the design, we'll give you an understanding or deep review of all these different kinds of bar. There is another question, what are the factors affecting partial safety? Okay, partial safety factors, whether if it is factor of partial safety factor for dead load, partial safety factor for load, then it depends on what kind of load you have, whether dead load, imposed load, wind load. If it is partial safety factor for material strength, then it depends on which material you are dealing with, whether it's a concrete, whether steel. Concrete is, because the uncertainty in concrete is more, that's why the partial safety factor is more. Uncertainty in steel is less because it is manufactured in a very controlled environment, that's why partial safety factor for steel is less. Okay, now the concept of partial safety factor we don't have as it is in other design philosophy. In reinforced concrete structure, we have only two material, concrete and steel, that's why the safety factor for material strength are discussed only for these two materials. Okay, let us now start some of the questions that I have not addressed now. I'll assure you that at the time of design, we'll address them. We address each of them. This is an interesting question, why beam idealization is required, and definitely we'll spend some time on that. Let us start limit state design of reinforced concrete beam. Okay, we have, this is the concrete, the matrix, then which is reinforced by steel, and we have different kinds of uh, two different kinds of steel bar. One is the longitudinal bar at the bottom, longitudinal bar at the top, and also these ties. Okay, I am not going to tell you what are these bars right now. As we proceed, this will be clear to you. You see, let us first describe the problem. There are two problems. Means we can. One problem is the forward problem. Forward problem is, if you remember the first slide that I showed, different steps you follow in structural engineering. The steps before design was analysis, and the outcome of the analysis was the forces and displacement in various structural components. The first problem is the design problem. Design problem is that you have analyzed the structure, so you know what are the forces in the structure. For instance, if you take a simply supported beam subjected to uniformly distributed load, from the analysis, from the structural analysis, we know that this is the bending moment diagram and this is a shear force diagram. The bending moment is maximum at the middle, which is WL square by 8, and shear force is maximum at the support, which is WL by 2. So these information we have from the analysis. Now what next we need to do is we need to design this beam such that this beam can withstand the maximum bending moment. This beam can also withstand the maximum shear force. You see, as I here the two different steel, one is longitudinal steel, one is this ties. We'll see later there's longitudinal steel. The purpose of this longitudinal bar is to take the bending moment or the stresses coming due to bending moment, and the purpose of these lateral ties are to take stresses coming from shear force. So we need to design the beam such that this beam can take this bending moment, and shear force both. And when we say designing this beam, everything we need to everything we need to decide. Only information I have the length of the beam. We need to design what would be the width of the beam, what would be the depth of the beam, what would be the reinforcement bar, how many reinforcement bars, what would be diameter of the bar, every parameters, everything we need to decide. And this is the design. So this is the forward problem. Okay. So problem description is we know the moment and shear force in a given beam. Now you determine the required reinforcement. Or in addition to that, one more thing is given we know the bending moment and shear force, determine the cross sectional dimension and also the required reinforcement. So this problem is the design problem. Another problem is called so this was the forward problem. Another problem is the inverse problem. It is determination of the strength of a section. Suppose I give you this design and I ask you, tell me what is the strength of this section. Strength of this section means how much bending moment or how much shear force this section or this beam can take. Here the problem description is we know the design of the beam, means we know the dimension of the beam, we know the reinforcement of the beam. Now with this information we need to find out what is the maximum moment and maximum shear force this beam can take. So this problem is called the, and eventually we need to find out that what is the maximum load this beam can take. This problem is called the inverse problem. Now to give you some example of forward and inverse problem, forward and inverse problem is very well understood because I need to build a structure. Before building a structure, it needs to be designed. So this is a forward problem. Now suppose there are many existing structure whose strength you need to determine. Okay, suppose the structure is 50 years old. Now you need to find out what would be the residual life of the structure. You need to, over this 50 years time, the strength of the structures already deteriorated. Now your objective is to what would be the residual strength of the structure. Okay, so you have the all the design information, and based on the information you need your purpose, what you are doing your problem is to determine the residual strength of the structure. This is, once you know the residual strength of the structure, then you can, if you find the residual strength is very less, then you can retrofit it. You can find out that it is beyond retrofit, beyond the retrofitting cannot be done, then you may have to change the structure. So assessment of existing structure is important, and this assessment is inverse problem. Okay. Now we'll discuss both of them in this lecture series. First, let us so since we are talking about beam, there are two major forces we have. One is bending moment and one is shear force. I believe that you know how to calculate bending moment and shear force for a given. Now you see this is very interesting. As I said at the beginning, after this lecture series, if you understand the mechanics which constitute the basis of this design philosophy, if you understand that, even if you don't design any problem, any structure, but if you understand that, I believe that you are ready. You have already set the platform to learn on your own. Those who are having concrete lab, they probably have seen this. This is a very interesting. You see, what is this problem? We have a beam here, and which is subjected to some load, 2-point load, one concentrated load here and another and then the beam bends, and when if you keep on increasing the load, then you will reach a time when the cracks develop. Now you see these crack patterns are interesting. You have two different kinds of crack pattern. One is which is near the middle of the midspan of the beam, which is almost go towards the support. This vertical crack becomes inclined, and if you add this support, it is very, and it is observed both the stresses which cause this crack to form, they are different. The governing stresses are different. These vertical cracks are primarily because of bending. The stresses that is caused due to, whereas these cracks, the inclined cracks at the support, the stresses, these cracks are formed due to stresses that caused by. Now if you go back to this slide, a simply supported beam, we have shear force is maximum at the support and bending moment is maximum at the middle. Therefore bending stress will be maximum at the middle, and if you go towards the support, your bending moment is 0, means bending stress is also. Whereas in this shear shear force is 0 at the middle, therefore your shear stress is 0 for this loading condition. If you go towards the support, your shear force is maximum, therefore shear stress is maximum. Okay, so we observe the incline crack at the support because shear, it is generated primarily because of the shear stress, and at the middle your shear stress is 0, bending is maximum, you get a crack which is governed by bending stress, that's why it is. So uh, we need to design the structure both for bending moment and shear. Now let us decompose the problem into two parts. This is the actual problem where we have both shear force and bending moment. Let us decompose into two problems. One is, it is purely moment, uh, not purely moment, primarily moment, and another part is we design it for shear and then we combine them. So the idea is, we first design this longitudinal bar which is primarily take the bending stress, and then we design these ties. The purpose of these ties is take the. So let us fix our sign convention. This is very important because if you are free to choose any sign convention, but whatever sign convention you use, please be consistent with that sign convention. But there is a standard technique, the standard sign convention that we take is, which is subjected to load, vertical load downward, then it deflects like. Now the bottom fiber, this is your neutral axis, means the axis remain neutral, means at this axis your stresses, bending stresses are 0. If you go above this axis, the portion of the beam is under compression, and below this your sign of the bending moment is there. So this is called bending moment, which causes sagging of the beam. It is called sagging moment, which we consider positive. Now the bending moment, the direction of the bending moment which causes hogging in the beam, which is called. Similarly, the shear force convention, your convention, sign convention for shear force. So this is the sign convention we will follow throughout this lecture. As I said, you can use your sign convention, but whatever sign convention you use, please be consistent with. If you mix the sign convention, then you will be in a great trouble. Okay, so the reason is, if you take this as positive, this bending moment, the positive bending moment causes tension at the bottom, compression at the top. But if you take this as positive, then this bending moment causes tension at the top, compression at the bottom. Since you need to also tell the location where reinforcement bar is to be given. Reinforcement bar is to be given only at the tension phase to take care of tension. So what sign convention you use, that is very important. So please be stick to that. So first we'll start design of beam for bending or flexure, and after that we'll see how it can be designed for shear. So our sign convention is, now for the time being, this is the sign convention we are in. Okay, this I believe that you all know that if we take a beam, which is subjected to sagging bending moment, means which causes sagging in the beam, then this is the neutral axis. Neutral axis means, as name suggests, the axis which remain neutral. Okay, there is no deformation in the axis, there is no bending stress in the axis. But if you move above from the axis, it is under compression. If you move beyond, then it is under tension. So what we need to do is, ideally, we don't have to provide reinforcement at the compression phase, because concrete itself can take compression. We need to provide reinforcement at the, there are cases where we put reinforcement at the top as well. Those cases we'll discuss later. That is called doubly reinforced beam. We'll discuss that later. So you see, from this onward, the next few slides, I'll go very slowly, and you please try to understand these slides, because these are the slides. From these to next few slides, they are the foundation of the limit state design philosophy. If you have understood these slides, then you have understood the major portion of the design. Okay, you see, this figure I have already you have already seen this figure towards at the beginning of the presentation. This is subjected to transverse load, and these yellow dotted line is the neutral axis. So beyond this portion is under compression, this portion is under tension. When it is subject to tension, the crack develops at the tension phase, because concrete cannot take tension. and this tension will be taken by. Now you see, if I take a section here, this section is since concrete, so this is the neutral axis. Above the neutral axis we have concrete which takes the and below the neutral axis there is no concrete, because the concrete cannot, it is assumed that concrete, you take any theory, any method, anything, they are based on certain assumptions. Knowing the theory is important, knowing a method is important, but more than that, understanding the assumption of that theory is very important, because if you before study of any method is incomplete until and unless you understand the assumption which constitute the basis of that. It is the assumption which tells you the restriction or limitation of the theory as well, because a theory is based on certain assumption. A situation where those assumptions are not applicable, the theory itself is not applicable. So it is very important you understand the limited design philosophy for flexure. The first assumption, if you see IS 456 code, these assumptions are given in different order, but I am giving in a different order so that we can have a better understanding. First assumption is tensile strength of concrete is ignored, means below the neutral axis, whatever concrete you have, it cannot take any tension. Since it cannot contribute anything towards the strength of the structure, no matter whether we have that part of concrete or not. So therefore, we remove. So neutral, above the neutral axis, we have concrete which take the compression. Below the neutral axis, assume there is no concrete tension, whatever tension you have, that is only taken by. Let's the width of the beam is B and overall depth is capital D. XU is the depth of neutral axis and small d is the effective depth of the beam. What is effective depth? Effective depth is the overall depth and the effective cover. Effective cover is you cannot put the reinforcement at the outermost fiber. You have to put the reinforcement, you have to give some cover, and that cover, the distance from the outermost fiber to the center of the reinforcement is called the effect, and distance from the outermost fiber to the face of the reinforcement is called total depth minus effective cover gives you the effective. How much cover you give in a structure, that depends on many things. That depends on what kind of structure you are designing, whether it is a beam, slab, column. Every structural component requires different. It also requires the environment the structure is subjected to. If the structure is subjected to a very adverse environment, which has potential to corrode the reinforcement, then we need to provide more cover. For instance, if you are designing offshore structure, then you need to provide more cover. If you are designing, say, foundation, you need to give a more cover. So cover, how much cover you give, that depends on many parameters, depends on whatever structural components you are designing. The structure is subjected to which environment. IS 456 has a detailed discussion on cover for different structural components and for different environmental exposure. Okay, so the first assumption is the concrete cannot take any, and AST is the area of reinforcement that you give. For illustration purpose, I have given 3 dots here, 3 steel, but it not necessarily mean that you have to provide 3 longitudinal bar. You can have any number of bar. The total cross sectional area is, those who are, you might have course on strength of material and mechanics as well. You know the Euler-Bernoulli's beam. The Euler-Bernoulli beam assumption is when a beam, you see, if you take a beam, thing is, you see, consider a beam here. When this beam deform, if you take this cross section, suppose these blue dots is a cross. After deformation, this section actually takes this shape. So this section which was initially plane, not necessarily remain plane after deformation. And it is true when you're when this structure, when this beam undergoes very severe. One of the assumption in limit state design is section which is plane before bending remain plane even after bending. So we assume that if the blue dots, this is the initial undeformed configuration of the beam, and after deformed configuration, the deformed configuration will take the green dot. The section which was plane remain plane. You can see here also, if this is the beam section and these two cross section, initially they were plane, and even after bending, they IMaintain. This is a very important assumption. This assumption you probably know. This is one of the important assumption in Euler boundary beam theory as well. But what is the consequence of that? The assumption is not that interesting. It is fine. The interesting is the consequence of that assumption. This assumption makes our life easier. You see, if the section is plane and after bending also section is plane, then what happens? Your strain, the longitudinal strain is, but sorry, this red line as your cross section, then longitudinal strain is not linear. The longitudinal strain is non-linear. But if you stick to that assumption that plane sections remain plane even after bending normal to the neutral axis, then the consequence of that assumption is your strain profile across the depth is linear. Okay. So this is the neutral axis where your strain is 0, and this is the compressive strain at the topmost concrete fiber, and this is the tensile strain at the center of the reinforcement. So this depth is the effective depth. After this, whatever calculation we make, it is in terms of effective depth. When we say the depth, implicitly I mean it is effective depth only. So the next assumption comes directly from the idealized stress strain behavior of concrete. We have already discussed this idealized behavior, right? That up to 0.002 strain, your stress strain behavior is parabolic, and beyond that it remains constant, and then at 0.0035 it fails. It fails in compression. So maximum strain we can have is 0.0035 irrespective of the grade of, we have already discussed this. So the next assumption is, which directly comes from this idealization. I won't say assumption, it is an idealization, that the maximum strain in concrete at the outmost compression fiber is 0.0035, which directly comes from this. So somewhere in the middle, maximum it is 0.0035. At the neutral axis, your strain is 0. So somewhere at the middle, your strain will be 0.00. So this point correspond to this point, and this point correspond to this point. And the neutral axis, this point correspond to. So suppose this distance is x1, this distance is x2. Another important thing comes from this figure is what it says, that from 002 to 0.0035 your stress is constant, and from 0 to 0.002 stress is parabolic. So from 0 to 002 on this section your stress will be parabolic. So in x1 stress will be constant, and in x2 stress will be. Let's see the next assumption. Next assumption also comes from, again this directly comes from the idealized stress strain behavior of steel. Somebody asked that if we know the strain, how to determine the stress. Yes, this is we discussed that, but again recall that question, that discussion as well. You see, this is the 0.2% proof stress. So this is your yield stress. Okay, this is your yield stress. Now what will be the strain at your yield stress at the characteristic load? Strain will, this portion is linear. This portion is linear, and slope of this curve is your Young's modulus. Okay, so this distance will be what? This distance will be your stress divided by Young's modulus. And what is this stress? Stress is 0.87 Fy. Why 0.87 Fy? Because it is Fy by 1.15. 1.15 was the partial safety factor for steel. So it becomes 0.87 Fy, which is the design strength of steel. Characteristic strength is Fy. Design strength is 0.87 Fy, which is Fy by 1.15. So this stress is 0.87 Fy divided by Young's modulus, give you this strain, and this is 0.002. So your total strain, this strain becomes 0.002 plus this, means 0.002 plus this. But read these assumptions carefully. We'll come to this. What is the basis of this? What is the reason for this assumption? This assumption says the maximum strain in tension reinforcement in this section shall not be less than this. It doesn't say that maximum strain is, it says maximum strain shall not be less than this value. Means your strain at this fiber should be greater than 0.87 Fy by ES 0.002. For the time being, you take it for granted and put a star mark here. We'll come again on this assumption why it is shall not be less than this value. Why not it is exactly this value? Okay. We'll come to this again. For the time being, you take the assumption for granted that this strain should not be less than this value. Okay, so shell should be greater than this. Next assumption is let us draw the uh, we also again this comes directly from this curve. We have already discussed that compressive strength of concrete in structure will be 0.67 times of the characteristic strength. That also we discussed why, and then on in addition to that we have partial factor of safety 1.15, which is more than steel. So we also discussed that in x1 your stress will be constant and x2 your stress will be parabolic, which is as this graph. Up to this is parabolic, up to this is constant. And what will be value of this constant? Value of this constant will be 0.67 FCK by gamma m. Gamma is 1.5, so it becomes 0.446 FCK. So your maximum stress will be 0.446 FCK. So this 0.446 FCK is essentially this value. Strain, what is the design strength at ultimate strain? So 0.0035 strain, your stress is this 0.446 FCK, this is 0.446 FCK. This is your next assumption. Now, next is since you're below the neutral axis, we assume there is no concrete because concrete cannot take any tension. The entire tension is taken by steel. If cross sectional area of steel is AST and design strength of steel is 0.87 Fy, again this is Fy by 1.15. If it is 0.87 Fy, then your total tension will be 0.87 Fy into AST. Okay. So this will be the total area of this curve will give you the total compression on concrete, and this stress multiplied by the area of steel will give you the total. So these were the assumption for Lemmy-State design philosophy. Now you see, if you have understood this, the strain and stress diagram shown in the box, if you have understood this, then believe me, you have understood a significant portion of Lemmy-State design of beam at least. Okay. Next is just the how this strain and stress diagram can be used. Okay. Now, any questions? Other questions? Okay, there is a question, or rather very interesting question. How does the incline crack occurs due to shear force? You put a star mark. Will shortly come how to design a member for shear force, and there we'll discuss this question in detail. How these incline, why the cracks are inclined due to shear force. In which cross section neutral axis is at 0 or minimum? In which cross section means? Okay, I have not understood the question. In which cross section the neutral axis has 0 or minimum deflection? Could you please, whoever asked it, could you please elaborate this question? And we'll come to this question once again after this lecture. Okay, why we take more factor of safety in concrete as compared to steel? Just now I said that steel is manufactured in a very controlled environment, therefore uncertainty in steel, strength in steel is very less as compared to the concrete. Concrete we cannot concrete we cannot make in a very controlled environment. There are a lot of uncertainty from where you procure the material, how much water you mix, what is the quality of water. Okay, it is very difficult to control each of them. So the uncertainty is more in concrete, and that's why the partial safety factor is more in concrete. Okay, now let us if we have any other questions as for in any other questions related to the assumptions, will come will come again. Now, this is a very important slide. You remember just now I said the assumption was, one of the assumptions was the maximum strain in steel should not be less than a certain value, right? 0.87 Fy by ES plus 0.002. I ask you to take it for granted and we'll come to this point once again why it should not be less than that value. You see, here we have two material. One is concrete and one is steel. It is fine that concrete takes the compression and steel takes the tension. But the behavior of concrete and steel, they are very different. The way they fail is very different. You see here, I have given stress strain behavior of two different material. One is brittle material, one is ductile material. Now, before I explain you this curve, I would like to show you two videos, one for or two videos on experiment, one on brittle material and one on ductile material. One is on graphite, which is again a brittle material. Another one is on steel, which is a ductile material. Let us, which one? Video sharing, right? You see, this is the compression test on a brittle material. It's around 1 minute video. You see how it fails. You see the load is increasing slowly. Okay. You see how what happens exactly. You increase the load, but you don't see any sign of failure. And suddenly, when load reaches a certain value, and it breaks. All of a sudden, it fails. Means in this case, the failure is very sudden. Before it fails, you really cannot assess. It's very difficult to assess, or very difficult to foresee the failure. It does not give any sign, or it hardly gives any sign before it fails. Now, compared to this, see another video on ductile material. This is tensile test on steel rod. First one was the compressive. You see, I don't know whether the video is clearly, you can see the video clearly or not. You see there is a neck is formed here, and in your solid mechanics or strength of material lab, probably you have done this experiment. If you keep on increasing the load, then a neck forms, but still it is not, it has not failed. A deformation is localized at a particular point, and because of the localization, the localized stress, this neck is formed. Now you see neck becomes more prominent here, but still it has not failed. It has become more prominent, but still it has not failed. Still it has not failed, and it failed. Okay, now you see the difference, and if you appreciate the difference, if you understand the difference, many of the concept in design will be clear. The first one was compressive test on a brittle material, where you increase the load and it fails suddenly, and before it fails, it hardly gives any sign. Whereas in ductile material, whereas in steel, when it is subjected to tensile test, then before it fails, it gives you some warning. In this case, the warning in terms of localization of deformation. So whenever if you see there's a localization, the localization has already taken place. Now you can predict, okay, then this is going to fail very soon. So it gives sufficient warning before it fails. Then what is the advantage income when we design a structure? You see, we always want a structure give sufficient warning before it fails, so that we can take some safety measures. But if the structure fails all of a sudden, then hardly we won't be having any time to take safety measure. That's why we want our structure to be more ductile. So when you design a structure, you design in such a way that your structure is more ductile. Now you have a two material here. One is steel, one is concrete. The behavior of concrete is brittle. The failure of concrete is brittle in nature. The failure in steel is ductile in nature. Naturally, if concrete fail first, then what happens? This fails suddenly. So therefore, uh, we really don't have any time to take any precautionary measure. But if steel fail first and concrete remain intact, remain unaffected, then what happens when the steel fails? Before it fails, it has to undergo severe deformation, and from this deformation, you get sufficient warning that that can be useful to vacate the structure or to take any precautionary measure. So therefore, our goal always is to allow the steel to fail first, not the concrete. So we want our structure to be more ductile. This is the stress strain behavior of steel. This is the stress strain, is a typical stress strain behavior of any ductile material. This is the typical stress strain behavior of concrete, okay, or any brittle material. And you can see that when it reaches the ultimate load, it suddenly fails. But whereas in ductile material, it reaches the ultimate load, then it undergoes severe deformation, okay, and then it fails. So this is the time during this deformation you get sufficient time to take all the safety measures. Now go back to the assumption. These assumption, no, not this assumption. These assumption. Tension reinforcement, the strain in tension reinforcement should not be less than this value. Why? Because the limit state of steel reaches the steel reaches its limit state when strain becomes 0.87 Fy by Es plus 0.002. When strain becomes this, the steel reaches its limit state. Now you want steel to fail first, means you allow more strain in steel. You allow steel to reach its limit state, because if your strain is less than this value, then steel will not its limit state, therefore steel will not fail, the concrete will fail. But you want steel to be fail. Therefore, you allow the strain in steel more than the value that it can take, and this ensure and this is the reason why this assumption, which allows a structure to be more ductile. Okay, I believe you understand these assumptions. Okay, now this is the last slide for today, and after that we have some interaction session, and you can address your questions as well. So we have seen there are two different kinds of failure. One is brittle and one is ductile failure. Brittle failure is when concrete reaches its limit state first than steel, and the ductile failure occurs when steel reaches its limit state first than concrete. Now, depending on which one reaches their limit state, we have three different kinds of. One section is called balance section. Balance section is where concrete and steel, they both reach their respective limit states simultaneously. Means concrete and steel both fail together. Okay. Another one is under reinforced section, where steel reaches its limit state first and therefore failure is ductile. And another one is over reinforced section, where concrete reaches limit state. Concrete reaches its limit state. There is grammatical error. Concrete reaches its limit state first, and therefore failure is brittle. Ideally, we always go for under reinforced section because we want our structure to be ductile. We can have section balance section as well. It is the economical section, but we cannot afford to have a section over reinforced. Now, why it is called under reinforced and why it is called over reinforced, for the time being, don't think that. We'll discuss that. Why it is called under reinforced, why it is called over reinforced. But the take from this slide is we can have three different kinds of section. One is the balance, where your steel and concrete, they reach their limit state simultaneously. One is a section which is ductile, where steel reaches its limit state first, and another one is brittle, where concrete reaches its limit state first. We don't want a section to be like this. Okay. So what we'll do next is we'll start with balance section. What is balance section? And then derive the equations for balance section, and then from balance section we'll deduce what happens when your section becomes under reinforced and why it is called under reinforced, and we'll also see what happens when your section becomes over reinforced and then why it is over reinforced section. Okay, so today we'll stop here. Next day we'll start with analysis of balance section. Now let us see what are the questions you have and then we can discuss them. Why are the parabolic variation of stress and strain? Somebody asked, why are the parabolic variation of stress and strain in stress strain curve for concrete? You see, that is obtained from experiment. As I said, the motivation or everything that we use, that are the motivation came from experimental observation. It is observed the concrete behaves like this, isn't it? So if the material is steel, then it behaves like this. Okay. So this is obtained from experiment. Well, there are reason to we can justify this variation depending on its microstructure, how the interaction of your aggregates or different components of concrete, but those things are more towards material science. But as far as design is concerned, these are obtained from experiment. Why is the compressive strength of concrete is considered 0.67 of FCK? Okay. See, when we test a concrete in a lab and use the same concrete in actual structure, you won't get the same strength. Okay. This effect of size on the strength is called size effect. Size effect is a separate study. In fact, there is a book by Bazant on size effect on concrete. There is a book on it. So there are different reasons for size effect. There is a statistical size effect. There are energetic size effect. We won't go into details. But the point which is important is the strength does not remain same. If you use it in actual structure, it gets reduced. So we need to reduce it. Now it is observed over the years that the reduction is, you take the 2/3 of the strength that you obtain from experiment. That's why it is taken 0.67. How the stresses are determined in steel? Okay, how the stresses are determined in steel, we have not really yet done the analysis. Let us do the analysis first. But to answer your question, we calculate the strain first. We know the strain diagram. We calculate the strain first, and from the strain we calculate the stress from stress strain behavior. But this exercise we will do tomorrow when we analyze the section. Below neutral axis in RCC, can you provide a lean concrete compared to compression fiber? Well, if I understood your question, your question is something like this. Since below neutral axis,
Hello. Hello.
okay, fine. Yeah, just 1 minute.
Hello.
Let me address this question.
Are you able to hear?
If I understand. If I understood your question is, since below the neutral axis anyway we are not assuming strength of concrete, so can we have a very low grade of concrete below neutral axis? Well, we really cannot. We'll discuss over reinforced section. We'll discuss, for instance, if I give you suppose a structure is under earthquake load where the stress reversibility, The compression fiber, depending on the direction of earthquake, the compression fiber may become tension and the tension fiber may become compression because of the reversal of load. And in addition to, there is a practical problem as well. You need a proper bonding also between steel and concrete, which cannot be really achieved by low grade concrete. So for all this reason, it is not a desirable as of now. But another important, having said that, I also mentioned that there are research going on where people are trying to optimize the material used. Probably that is a good concept. The further research or further investigation may be required. Why the value of strain in concrete is more than the steel? It's not that value of strain in concrete is more than steel. Value of concrete is 0.0035 irrespective of the grade of concrete, but value of steel depends on the grade of steel. For different grade of steel, you have the value of strain different. In fact, for instance, for Fe415, the value of strain is around 0.0038. If it is 500, then value is higher than that. It's not that it is smaller than value of okay, why the size of cover varies in beam, column and slabs? Okay, you put a star mark on it on the last day when we talk about extension of the beam concept to higher to different structural component. Then we discuss briefly, very briefly, the modification required for column and slab and staircase. We'll discuss this question definitely during that time. Yeah, hello.
Yeah, hello. Are you
Yeah.
able to hear me, sir? Yeah.
Yeah, I can
This
hear you.
is
I
from
can
the
hear you.
Central Indian College.
Oh, hi.
This is from the Central Indian College, Badalpur.
Okay. Okay.
Okay. With regards to the factor 0.67, what
Yes.
you mentioned as the size effect, reason as the size effect.
Yeah.
But what I understand that there are two factors for that. One is the size effect and another is the confinement and non-confinement. Because in a real structure you have confinement concrete, but in a cube when
Yes.
you are testing it, there is no confinement. So one is the
Yes.
factor of 0.8 and another is factor of 0.85. The product of those two is 0.67. Is that right? Or
You see, because of confinement, actually, what happens? Your because of confinement, your strength, the ductility increases. Okay. For instance, if you take a cylinder, okay, and test it, and then you confine that, you wrap something on that cylinder and again test it, what you will see that because of the wrapping, even the structure fail, but it doesn't, even the cylinder fails, but it doesn't collapse. So you will get more ductile behavior. So confinement effect is anywhere there. Confinement, it increases the ductility of the structure. But when I say the size effect, it is a very general term, uh, or more precisely, probably we should say it is size and shape effect. It's a very general term. Uh, it tells you the change of strength when you increase or decrease the size of the structure. Now it has several components, and probably confinement, the components that you say, that's one of it. When I say size effect, it is, I try to mention everything, combining everything together. It is the effect of size of the structure. But confining effect is certainly increases the ductility of the concrete, and it is better to have. In fact, you will see there are some research going on where people use FRP wrap on concrete. Okay, they try to reduce the reinforcement, and that is compensated by FRP wrap. What is the reason for FRP wrap? Because you confine the concrete so that it gives you more ductility. This is the confinement you are talking about, or you are talking about some other confinement?
no, when we test a cube in the laboratory,
Yeah.
it's free on all sides, except that we have a load on the top and bottom we have a platen. But whereas
Yeah.
in a real structure, when you take out a cube or when you analyze a cube within the beam or any particular structure, you have the concrete surrounding it. Will
Okay.
that also be a reason that when we idealize the things and take the design strength as 0.67 times of the characteristic strength?
Yeah, that's what I'm telling. Concrete surrounding is means what? Means your structure is larger, right? Structure is larger, right? So that is this effect of the size of the structure. See, the thing is, I can tell you one small example. Okay, it is just to demonstrate, right? I mean, it's not that exactly it happens. Suppose you take a structure. Okay, it is one of the reason for size effect. You have several flaws in the structure, right? Several small cracks, micro cracks in the structure. Now, what you do is when your structure is larger, the probability of having the number of flaws also increases. Okay, so more number of flaws you have in structure, it is more prone to failure, the less strength you have. So this is one reason of size effect. So when I say size effect, I really size effect is a separate story. There are, as you say, there are concrete surrounding it. These are all the reason for size effect. But the point is, it is the effect of size that is the reason why we reduce the strain. The size effect may be caused by several factors, as you mentioned, your the presence of concrete surrounding it, presence of more number of floors. Since the size is large, the structure has more capacity to store energy, and every crack to propagate, it needs energy. The more bigger the structure, more the energy availability of the energy, so crack can easily propagate. It takes the energy from the stored energy. This is the energetic size effect. So these are the various reasons for size effect. I'm not going into the reason for size effect. What I want to say is, because of the size effect, this strength is reduced. What you are saying is that these are different components, different reason for size effects.
Hello, sir. So, if stirrups not play a major role in bending moment, is it not necessary to provide stirrups in middle section of the beam?
It is not necessary.
To provide the stirrups at the middle section of the beam, where there is
Okay,
no shear force. Shear force is zero.
okay. When we discuss the shear, we'll discuss as well. Even the shear force is zero, we need to provide a nominal shear. Even the shear force is zero, theoretically, even if it is zero, we need to provide some nominal shear force, some nominal shear reinforcement. And that's true for any, even if the bending stress is very small, we need to provide some nominal, there is a minimum reinforcement, both bending and as well as for shear, that needs to be provided. Even your bending moment is small, even your shear stress is zero at the mid section. And why that minimum shear force needs to be provided, that also we discuss when we design structure for shear stress. Let that comes. Let us first discuss what is the effect of shear stress, how the crack obtained due to shear stress. Then definitely we'll address your question.
Okay, thank you, sir.
Good afternoon, sir.
Yeah. Good afternoon.
Good afternoon, sir. It's Akash from GNE College. I have to ask that the cracking of beam is governed at the middle by bending stress, bending moment, but at the side by shear force. Why?
Okay. Actually, we have not really yet discussed the effect of shear force. Okay. I gave you the picture. Let me first come to the effect of shear force. Definitely, on that I'll tell you why the cracks are inclined and how the cracks are formed due to shear force. But just as you have asked this question, can I have this document camera on, please? You see, suppose you take a block like this, okay? And suppose these are the shear force acting on this block. Okay. Now what happens? What is the effect of what is the resultant of these two shear force? These two shear force will cause, this is the resultant. This is the resultant of this shear. Similarly, resultant of these two shear stress is this. Resultant of these two shear stress is this. Now what happens if you take two diagonal? This is one diagonal. This is another diagonal. Now, on this diagonal, you have tension because of the resultant of this shear. But on this diagonal, you have compression because of this resultant. So naturally, if this concrete is strong in compression but weak in tension, the crack may propagate like this. This is the reason why you have inclined crack, but we'll discuss the same mechanics again in details when we talk about the effect of shear. But this is just to answer your question. This is the primary reason.
Thank you, sir.
Is this clear, or you need some more clarification?
Clear, sir. Thank you, sir.
Hello.
Clear, sir. It is clear.
Okay. Thank you. Okay. Do you, anyone? Is there anyone having any question?
No, sir.
Okay. Then we can connect to other center. Yes.
Sir,
Yeah, I can hear
sir,
you.
I just wanted to ask that why 150 cube is used for compression. So why 150 cube is used for compression test? I'm asking, sir, 150 cube we use for compressive strength testing. So why 150 only?
Okay, then what do you think 150 mm is more or less? 150 mm is more or less?
So I think it's less because and also sir, why cube? Like if we use curved member for a structure, so it might be possible that strength may vary or the failure may vary.
You see, there are two things. One is the strength of a material, and the another one is strength of structure. Okay. For instance, suppose if you take a brick, okay, brick has got some strength. Now, if you stack brick without putting any mortar in between, then you have a structure which is made of some brick stack, right? If you push that wall, it will easily come down. Okay. Now, every component, the building blocks of that structure was strong. The brick is strong, but the strength, the structure did not have. The structure does not have audio muted. Structure does not have the sufficient strength. So, what you are telling, you are combining these two things. Making while we test a concrete cube or a cylinder, or for that matter any specimen in laboratory, our objective is to, can they hear me? Can you hear me properly?
Yes sir, yes sir.
Yeah. So when we test any specimen in laboratory, our objective is to find out the strength of the material. Okay. Yes, the material strength may vary when it is used in real structure, irrespective of the your shape and size of the structure. And that's why this effect of size, effect of shape comes in. Okay, so we cannot, suppose I want to use a particular grade of concrete in a dam. I cannot make the entire dam in laboratory and test it, right? It is not feasible. What we do is, I test the concrete, the strength, the material used for the dam, and yes, because of the change in shape and size and because of their effects, we need some modification of the strength when the same material is used for actual structure. Okay, even the even the structure is curved, even the structure has any other shape. Our role in laboratory tests is to find out the material strength. Okay, not the structure strength.
So we are assuming assumption as neutral axis deflection is 0. Apart from this assumption, which shape of section has 0 or minimum deflection?
Which kind of section has minimum deflection means? I didn't get your point. Means what is the shape of the section?
So
So
we
that
are assuming.
yes, I can
Hello,
hear
sir.
you. Tell me.
Am I audible?
Yes, I can. Yeah, I can hear you. I can hear you.
So we are taking assumption neutral axis deflection is 0. Apart from this assumption, which shape of section has minimum deflection?
Okay. The first of all, neutral axis
Which
assumption.
shape of section has neutral axis minimum deflections?
Any axis. See, when we say neutral axis, the name is, it is the axis remain neutral, right? So you take any section you take, the axis which remain neutral, that is your neutral axis, and that at that axis your strains and bending stresses are zero. Okay, you can have neutral axis in any section. Okay, any section. You can have neutral axis In some cases, for instance, some cases in column we can have neutral axis outside the section as well. But the axis where your strain and stresses are 0, axis which remain neutral, that is the neutral axis. Any section you take, the neutral axis, strain and stress is 0. That's why it's called neutral. For instance, some cases in column we can have neutral axis outside the section as well. But hello? 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 Hello?
Hello, sir.
Yes, tell me. Hello?
Repeat the
Yes.
solution, sir.
Hello?
Hello, sir.
Yes, tell me. Yes. I mean, if you don't get confused, neutral axis strain and stress is 0. It is not assumption. I mean, if you don't get confused, neutral axis theory, right? Strain and stress is 0. It is not assumption. If the bending is positive, top fiber under compression, bottom fiber bending is positive. So in between you have a full compression, bottom fiber stress is 0. In between you have a full neutral axis. Neutral axis stress is 0. It is not an assumption in limited design. Stress is 0. It comes directly from the theory of beam. Nowhere we mention, we have discussed many aspects. Nowhere we mention that stress at the neutral axis is 0 is our assumption. It's not our assumption. It's not our assumption. Is it, I mean, does it answer your question? Does it answer your question? Or if I have not understood your question, then could you please have our email ID? Could you please write question in more detail so that I can give you an elaborative answer? Maybe I have not understood the question. Properly. Please write to us. You see, there was a question that where we use working stress method in practical. Still we use for some structure. For instance, in limit state design, we allow some amount of crack in the building. Okay, the limit that comes in limit state of serviceability. If you remember the slide I showed you, and the corresponding clause also which talk about how much crack is allowed as per limit state design philosophy. But there are some structure where any amount of crack you cannot afford to have. For instance, any water retaining structure, offshore structure, you cannot really allow to have any crack. So there are some cases really we still use. Okay, since no one is having any question, so I'll stop here. Tomorrow we'll start with design of or the analysis of balance section, and from analysis of balance section we'll go to see where the section becomes under reinforced and where it becomes over. With this, I thank you all.